We're live. Howdy, howdy, howdy. Getting ourselves set up here. Let's get this Windows stream. It will begin shortly. Getting myself set up. Extend. Exit Visual Builder. All right, let's get. Nope, wrong button. Okay. Oh, the screen share isn't working. Sorry about that, y'all. I forget that happens. Ugh. Okay. There we go. Screen share's happening. Let's do a sound check. Sound is working. Sound check. All right. And we got the website updated. Perfect. Okay. We're starting even a little early tonight. Okay. There we go. Oh, stream's lagging behind a little bit though. Nope. My feed just fell behind. That's on me. Howdy y'all. I'm Ryan. I'm the calculus tutor. This is our Tuesday night stream. I'm here answering your math questions. Pretty much simple as that. Top of the streams, we're repeating it until it happens. Abolish ICE, abolish ICE, abolish ICE. Get them out, impeach them, all of it. There are things happening at the federal building here in Eugene, Oregon today. From the reports I'm hearing, several protesters have been taken inside, later released. There were hundreds of people down at the federal building at various points this evening. If you were one of the people that got down there, appreciate it. Keep doing it. I want to keep getting down there too. All right. What do we got going on tonight? Oh, well, let's talk about how you do this. I answer your math questions. You can go to thecalculustutor.com/live if you want to ask math questions. to, let me show you that. Boom, boom, boom. Go back, tap the thing. Okay, so you go to calculustutor.com/live, and you'll see my page. There's a menu up top. You can submit math questions there. You can scroll down. There is a submit questions form here, or you can just email your questions directly to me, ryan@thecalculustutor.com. That form, you click on it, it's a Google form, loads right up for me. It will probably ask you to sign into a Google account if you're not currently signed into a Google account. If you try to use a school Google account and it won't let you in, it's just because your school has your Google accounts locked down. Email your question to me instead. But let me know what school district you're with, and I'll try to reach out and see if I can get my form whitelisted. But yeah, this is what I need from you. If you're going to submit a question, you have to, like I said, you have to be logged in. So this is just saying I know that you're recording my email address. Tell me who you are, just your preferred name, however you'd like me to refer to you on stream while I'm answering your question. You can put your pronouns there too. Tell me where the question came from. Just class and teacher is kind of what I'm thinking there. Mick Anderson's Algebra 2. If you're a college or university student, you don't really need to let me know the teacher, but you can. But Math 253, whatever. And then a place for you to ask your specific question. Now, your question might only be as specific as, can you show me how to do this? Totally fine. I'm absolutely happy to answer that question and show you how to do the problem you submit. But if it's more specific, I'm not sure how to deal with the fractions in this problem. I'm not sure. They're talking about a trig identity and I don't know how to use it. Things like that. That's a place for you to ask me your specific question. Also direct me to what problem you want me to answer, because at the bottom you can attach images. And so my idea is, if it's a textbook problem or a worksheet, just snap a picture of the whole page and send it to me. And so up here, yeah, you would want to tell me what problem it is. And if you can also attach a PDF. So if it's like online, one, you can just take a screenshot of the specific problem, but if there's like a whole packet, you can just send me the PDF packet. And in that case, probably tell me, page 3, number 28 or something like that, right? So just direct me to where to go, and then tell me what about that problem is giving you trouble. One other thing to include, if you can, is an image of any work you've already done on the problem. That actually really, if you've already done any work related to that problem, that can help clue me into how I can be the most helpful to you. Essentially, the more specific question you ask and the more detail you give me about the problem you would like help with, the more specific and detailed my help can be. But that said, you can just send me a problem or a set of problems and say, can you show me how to do these? And I'm happy to do that as well. Can I share your work on stream? Basically, I promise not to show your work on stream. There is a certain type of help that some people might need where they might want me to go through their math work line by line. That's there for those people, but that's not going to be most people. That's just like upper level math stuff. So yeah, that's how you submit a question. It's all just done through the website here. You can see the streams right on the page. The notes that I'm going to write are accessible at this button here, or under that heading there as well, math notes. And you can jump into the notes, move around, so you can see more than just what I'm showing on the screen. And yeah, I think that's what we got going on. Let's jump back to the notes. I do have some questions ready to go over. This is exciting. Some physics, some calculus-based physics, which is exciting. Let me grab those and get those going. Oh, it's doing the black screen thing again. Sorry about that. There we go. Okay. So I'm just going to sort of jump into these. Oops. Oh, there we go. So here is a question to get us started. This is a question that I'm working on with one of my one-on-one students. I do offer one-on-one tutoring. That's on my website, thecalculustutor.com. There's information about rates, and you can send me a message if that's something you'd like to request. All right, so let's see what we're working on here. Spore launch. We've noted in class that some fungi, like Pilobolus, can launch spores a considerable distance. Consider a Pilobolus that launches a spore with a speed of 25 meters per second at an angle of 30 degrees above the horizontal. The fungus is short, so consider its initial height to be ground level. There's a bush that's 70 centimeters tall, a distance 1.4 meters away. Will the spore run into the bush or fly over it? If it clears, by how much? Sure. I mean, if we're going to figure out that whether it clears, it's just a subtraction in order to figure out by how much it clears. So here, let's illustrate the problem, shall we? Give ourselves a little graph. And now this bush is going to launch a seed at some angle with, actually, we know the velocity. Here, I'm just going to call it VO for right now, V naught. And that seed is going to follow a trajectory like such. And we're wondering, there is a plant or a bush, right? So here's our bush. And it is a distance 1.4 meters away, and it has a height of 0.7 meters. So I took that 70 centimeters and just converted it to meters. And we want to know if it will clear it. So I don't know. I drew this parabola just in a general sense, and so this is sort of what we're wondering. Whenever you have a velocity like this, so this velocity is some arbitrary angle. What's really awesome is you can split this velocity into an x component, and you can split it into a y component. That x component, so I'm just going to do this right here, Vx is always equal. So long as your angle is from the horizontal, and that's why we standardize that, right? You'll almost always hear angles of elevation or depression given, which means they're always measured from the horizontal. The reason we do that is because if you do that, then to find the x piece of that velocity, what its velocity is strictly horizontally, you can always just multiply by the cosine of the angle. Similarly, to find the vertical component, the y component, you can just take that initial velocity and multiply by the sine of the angle. I need to throw a little zero on those. There we go. And now, check it out. We can kind of figure out a bunch of stuff out. Separately with my student, we made a note of the position. So the x position, or here, let's do a little bit of background here. This is a kinematic equation. So the general position, we use S for that, is -1/2 AT squared. Actually, we're not going to put the negative there. 1/2 AT squared plus that velocity times t plus some initial position, where the problem tells us we can consider the initial position 0. Right. The fungus is short, so consider its initial height to be ground level, so 0, which means we can our horizontal position is going to be acceleration in the horizontal direction, gravity doesn't work in the horizontal direction, and we're ignoring air resistance, so our acceleration is 0. Our x velocity, we already know that our x velocity is that velocity times cosine theta times t. And our initial position x, we'll just consider 0 because the plant, the bush is 1.4 meters away. So we'll consider the plant to be 0.0, and then this can be position 1.4 meters. And there we go. That is our equation that gives us the x position at any given time, right? So we could use that to say figure out how long it takes for it to get to this position. We also want an equation for the position in the y direction. Acceleration in the y direction is given by gravity. So we will rewrite this as negative g over 2. So acceleration is just g, and I've just multiplied it into the half for convenience. So times t squared plus v in the y direction is just v times the sine of theta, and then that'll be times t. And again, we're saying ground level, so our initial position is, y position is 0. So boom, we have these two equations. We can, since we know the x distance away that we're looking for, we can set x of t equal to 1.4 and solve for t. And that will tell us how long it takes this spore to get to 1.4. So that's what we'll do. We'll do 1.4 is equal to v times cosine theta times t. We can just divide out this to both sides. And so we get that t equals 1.4 over v cosine theta. We know what our v and our cosine and our theta are. So this is 1.4 over our v0 is 25 meters per second. V0 is 25 meters per second. There we go. And so we'll go 25, and we'll do times cosine. You know what? Since this is a physics problem, I guess we should do a good job of keeping track of our units here. So this is 1.4 meters. This is 25 meters per second times cosine is unsigned here. It's just cosine of 30 degrees. Right, it was 30 degrees. Yeah, 30 degrees. I guess I'll write that down up here too, just so we have it. Theta equals 30 degrees. So this is meters over meters. These meters will actually cancel. This is seconds in the denominator of the denominator, so that's going to flip up to the numerator and make our unit seconds, which makes sense because we're looking for time. So excellent. So we just have to do 1.4 divided by 25 times cosine 30. And so I'll just do that in a calculator. 1.4 divided by 25 times cos 30. I am in degree mode. Perfect. And so we get that t equals approximately 0.06. I'm going to call it 5. Excellent. There we go. That's actually probably more significant. That's way more significant figures than we deserve, but that's totally fine. It's an in-between figure. We'll keep it. This is seconds to reach the bush. You can see the next problem I want to work on down here. Let me get that out of the way. There we go. Remember, you can always access these notes from the website, so you can scroll around. That way, if I scroll something off the page, you can go back and look at it. You're absolutely also free to just let me know in chat. I try to keep my eye on chat. If you want me to scroll back up, or if you have a question about something that's scrolled off screen. All right. So there we go. Because we had a horizontal position that we knew about, that 1.4 meters, we could set that equal to our horizontal position equation and solve for the time. And so it'll take like less than a second, and also like less than a tenth of a second, but it's going it's not going 25 meters per second in this direction, but it actually, how fast is it going in that direction? Let's just multiply it out. 25 cosine 30. It's going almost 22 meters per second horizontally. So yeah, it's not going to take it very long to go 1.4 meters. Excellent. So now what we can do, I'm going to do? I'm going to take this over here. We're just going to move this around. We're going to say, I'm going to call this, oops, let's make it a little nicer. Step 1 is set x of t to that and solve. And now we're going to, over here, we're going to do step 2, plug t value from step 1 into y of t. So we know how long it takes it to travel 1.4 meters horizontally. Now we want to know, how high is it? What is its height? What is its vertical or y position at that time? And since we know that time, we can just plug it in. So we can just do y of, and we'll plug in our 0.065 value into this equation. And so we'll get, I'm just going to write it like this still, negative g over 2 times 0.065 squared plus v sine theta also times that 0.065. Sorry, writing a little bit small there. We can move that over, and then I can write that a little bit bigger. 0.065. There we go. And then, of course, we just need to plug in all the values that we know. Gravity is 9.8 meters per second squared over 2. Oh, our unit on this is seconds. So then we're going to multiply that by, well, actually, I'll do this. I'll go ahead and square this right now. 0.065. We're going to get 0.004 seconds squared. Plus, I'm going to bring this stuff down to the next line. Plus, our v there is 25 meters per second times the sine of 30. And then times 0.065 seconds. And so you'll notice some units cancel out here really nicely for us. The second squared cancel with the second squared, just leave us with meters. Seconds cancel with seconds, just leave us with meters. So we'll get these meters plus these meters, and we'll just have meters at the end. And so now if I plug this in to a calculator and compute it, y of 0.065 seconds is approximately equal to, so let me get that plugged in. 4.9 plus 25 sine 30, which is just a half, times 0.065. Excellent. What I get is 0.83 meters. All right. And so what we can say here, we can draw a conclusion. So we can now say conclusion. I encourage you, when you're working on problems like this, spell out your steps as step 1, step 2. It will help you learn the process, right? To subdivide it for yourself into these smaller chunks. And if you're struggling with the problem solving process for the whole problem, you can start to like narrow down where you're having the most trouble. Is you're like, wait, do I understand what's happening in step 1? And you sort of work through step 1 or look through notes about step 1 or something, and you're like, yeah, I totally do. I understand step 1. And then you're like, okay, so let's go to step 2. And you're like, oh, okay, no, step 2 doesn't make sense to me. And that can be really useful. That helps you like really sort of isolate where you're having trouble and then keep digging in, keep digging in. All right, so our conclusion is let's see. When the spore has traveled a horizontal distance, horizontal distance of 1.4 meters, it will be at a height of approximately 0. How many sig figs do we have? We have 2, so 0.83 meters. So yes, the spore will clear the bush by about 0.13 meters. Right? The bush was 0.7 meters tall. Yep, 0.7. And the spore is going to be at 0.83, so it will clear it by about 0.3 meters. And there's our final answer. Right? So what did we do here? If we go back, right? So we had to sort of understand how you decompose a velocity, a two-dimensional vector, into its vertical and horizontal components, is what we would call them. The horizontal, assuming your angle is measured from the horizontal, then the horizontal component will always be that initial velocity times cosine. The vertical component will always be that initial velocity times sine. Okay, we also needed to know our kinematic equation for motion, and then we can from there put together a kinematic equation for just the horizontal position and a separate one for just the vertical position. And they're obviously working at the same time. If we plug in a t-value, the same t-value, so say 1 second, or rather 0.065 seconds, right? Um, that will tell us into the x equation, that will tell us where it's at horizontally. And then at the same time, we can plug it into the y equation. That'll tell us where it's at vertically. And that'll give us the specific coordinate in space relative to this bush where it is. And so we said, okay, well, we know something about the horizontal position. And we can leverage that. I'm sorry, y'all. I need to take a break for just a moment. I'm very, very sorry. I'm going to mute this and I will be right back. All right. Oops, I knocked my camera. I am back, y'all. Yeah, that seems fine. Let's do a quick sound check, and we'll get back into this. Sounds good. Cool. Okay. Sorry about that. I do apologize for the interruption, but we are back. So, like I said, we need to know how to decompose a velocity into its vertical and horizontal components, but that's just as simple as multiplying by sine and cosine. We also need to be aware of our kinematic equation for position, and we can have a separate one for horizontal and a corresponding one for the vertical. Because we have information about a position we're curious about, we can set the horizontal position we're curious about. We can set the horizontal equation equal to that value, solve for t, and then we know at what time, how long it will take it to arrive at that position. Then once we have that time, what we're curious about is it at a height sufficient to clear this obstacle? So we plug that time into the y position equation, the vertical position equation, and that will tell us how high it is, the height of the spore at that time. We found that it was 0.83 meters, which is 0.13 meters above, or 13 centimeters above the top of the bush. So it will clear the bush. And there we go. And that's the value of splitting these vectors into components, right? Is you might know something about one dimension, but not something about another dimension, and you can work with them separately. It's really, really great. Okay, cool. That was number 3 there. So now we'll move on to number 4 here, archery. Oh, there we go. All right. You are watching an archery tournament and wonder how fast an arrow is shot from the bow. You ask one of the archers to shoot an arrow parallel to the ground. You find the arrow stuck in the ground 60 meters away, making a 3-degree angle with the ground. How fast was the arrow shot? So there's a couple hints here. Note that you don't know the starting height of the arrow. And number 2, the arrow's angle at the end tells you a relationship between the x and y components of the final velocity. For example, if Vx at the end and Vy at the end were equal, the arrow would make a 45-degree angle with the ground. Right. Okay. So we're going to be doing kind of an element of like working backwards from that arrow. So we have so I'm very much going to exaggerate that here. Let me exaggerate this just because we don't have a lot of room to work with, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Boom, right there. We're going to call that 60 meters. 12, which means each of these is 5 meters. Cool. So we have an arrow stuck in the ground at, obviously that's more than 3 degrees, right? But there's our arrow stuck in the ground, and it must have, so the archer was here, the archer was sort of back here, the bow, was here, and the arrow was launched from, some unknown initial y height. And it started off going horizontally, but obviously it's going to immediately start to drop. Boop. And there we go. Right? And we can see that if we trace this back, because it was fired horizontally, that's sort of the midpoint. And it has a constant horizontal velocity. Its horizontal velocity is not changing. So yeah, so this point right here is sort of the midpoint of this parabola. If this had been sort of shot from ground level to achieve the same result, it also would have been shot from 3 degrees, and yeah. Um, so in some ways, this is sort of just backwards. Um, ba, ba, ba. Oh, right. How fast was the arrow shot? We want to know what we're looking for is its initial velocity, or not VOT, um, its initial velocity. But that initial velocity is also its its x velocity. Um, it doesn't lose any x velocity. Um, okay. Ba, 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 ba. Okay. Okay. So, what do we know here? We have similar things. We know our x of t is still just going to be v cosine theta times t. Um, hmm. But the cosine of the angle from the initial position is actually 0. So this just works out to that, right? Because its initial velocity is actually right here. This right here is initial velocity, which equals v of x, right? That's its initial position. That's its initial placement, and therefore its initial velocity. And so that angle there is 0 degrees. Cosine of 0 is 1. So this all just simplifies to that for the x direction. The y direction, on the other hand, we do have gravity, so negative g over 2 t squared plus v sine theta t plus that initial y value that we don't currently know. Um, ba, ba, ba. Okay, sorry. I was thinking ahead. I apologize for the silence there. Okay, so we have this. However, again, the angle with the initial velocity is 0. Sine of 0 is 0. So this entire term goes away. And really, we're just left with this. That initial velocity doesn't have any impact on the y position. Only gravity does, and the initial position there. Ba, 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 ba. We know. Oh, okay. Hold on. We have 1, 2. We do. We have 3 unknowns here. We don't know our initial velocity. Well, actually, yeah, we don't know the time. The time is our variable here. Uh, and we don't know this y, so we need a third equation. So this is actually a useful thing. Uh, when you're solving an equation like this, or not an equation, when you're working on a problem like this, in order to solve for all the variables, you need at least as many equations as you have variables. Um, there's no if you have there's no way to solve for all of the variables if you have fewer equations than variables. Um, so we do need some other equation so we can sort of figure out a relationship here. Um, and this hint number 2 tells us to pay attention to that angle, and we haven't done anything with that 3-degree angle. I'm gonna not that shouldn't be theta, it should be 3 degrees. Sorry. That's a different theta than the theta that was in here. This is our initial theta, which is 0 degrees. For example, if Vx and Vy at the end were equal, the arrow would make a 45-degree angle with the ground. That's true. So essentially, what they're telling us here is so I'm going to extract this arrow. So we have some arrow, right, at some angle. And now the angle of the arrow at any given point corresponds to, so we can think of this as it had some total velocity, and then it had some x velocity. So this is our final velocity. And it had some y velocity. Oh, Vy, sorry. Vy, there we go. And this angle, which we know is 3 degrees, so we should be able to. Yeah, okay, I see what's happening. Well, so there's a couple things going on here, but essentially that arrow preserves for us the angle at which the arrow impacted, right? Like if you just threw a rock, it would be hard to see afterwards at what angle it impacted, but because of how arrows work, it preserves as it sticks in the ground, it preserves its trajectory angle. This is excellent. So what we know though is for any given angle, we have for this angle here, this is the opposite, this is the adjacent. So we know the tangent, the tangent of any angle is the opposite side of the triangle, the right triangle, over the adjacent side. So for us, this is going to be tangent of 3 degrees, which is just some number. We can plug that into a calculator to figure out what it is. And that's going to equal the opposite side is our Vy. Our final Vy, and the adjacent side is our Vx, our final Vx. Mm-hmm. Mm-hmm. And we know our Vx, okay, here we go. Oops. We know so this is tangent of 3 degrees is equal to Vy over that final y velocity. Vx, though, is just our initial velocity, right? That's one of the things we're saying. So Vo is equal to, oh no, Vy, ha 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 ha. The final Vy is equal to, we'll multiply that over, Vo times the tangent of 3 degrees, whatever that is. Ooh. But we know we can figure out what the final y is. Aha. Okay. I might be doing this in kind of a roundabout way, but like I did with the last one, once we've kind of figured it out, I'll go back and I'll summarize what our process was, to hopefully clear away any of confusion that arises in the problem solving process, right? Okay. Here's the thing. So this is the kinematic position, or the kinematic equation for vertical position, for y position. But there's other kinematic equations, right? We can figure out the velocity. Here, let me write this separately. Where do I want to write this? Sorry, I'm trying to figure out where I want to write this. We'll just write it right down here. We'll just sort of keep going. Velocity for time. So this is our general kinematic equation for velocity rather than position, is acceleration times t plus some initial velocity. So our Vy of t in our case is just going to be negative g times t plus and that's it, because initial y velocity is 0. So plus 0, right? Because this is horizontal, so initially it doesn't, the archer isn't shooting it up or down, shooting it perfectly horizontal. So it has 0 horizontal velocity. Or sorry, it has 0 vertical velocity. Pardon me. So yeah, so Vy, so we'll just simplify this and saying Vy is equal to negative gt. That's what we want. Okay, which means, so up here, instead of solving that for Vy, I'm going to solve it for Vo, which is going to equal, so when you're solving it, so we can multiply the Vo over and then divide by the tangent, so we just get Vy over tangent of 3 degrees, like that. And now we know what that Vy is equal to. Let me rewrite that a little bit better. Vy. Okay, so actually, y'all, I don't think we need this at all. Here, I'm gonna put it over here in case we do need it. And then I'm gonna let's bring this all back front and center. So, okay. There we go. Okay, so this is actually what we want. We want this. We talked about the tangent, where that came from. And then if we solve that, we get this up here. Vo equals the final y velocity, final vertical velocity, over tangent of 3 degrees. So actually, we'll put this back over here. So I want to make sure these notes also make sense later on. So hopefully I want the notes to be laid out in a way that sort of makes sense. I'll put this over here. Okay, so there's that. We also have, so this is our, so I'll move this over here. So this is our kinematic equation for speed, for velocity rather. Kinetic velocity, right? So this just tells you the velocity when at least in a straight line, this is how velocity works. It's just the acceleration times the amount of time plus some initial velocity that may have been there. Okay, so we're going to look at Vy specifically. So that's what this is. And Vy, I was doing green. And we'll make a note here. Initial vertical velocity is 0. Boom. Oops. Is 0. And so we end up with this equation here. Yeah, this equation here, which we can plug in over there. And we can say, okay, that initial, oops, that's not the color I wanted. That initial velocity is actually equal, oops, g times t over the tangent of that 3 degrees. And that's how this would always work. We sort of derived an equation. If you can know the impact angle, this is the equation that will tell you the initial velocity if that initial velocity is horizontal. I'm so sorry to do this. I do need to step away again. But I will be right back. I'll be right back and we'll finish this off. All right, back again. I do apologize. We'll do quick sound check. Sound check. Did I? Hold on. That's why. What? Sound check. Yep. That's why. What? Sound is good. Very good. Okay, back to it. Yeah, so we sort of we derived in this process. This will always give you the initial horizontal velocity based on the impact angle. Assuming that a launch angle is zero degrees. And now we can plug values into this. So negative 9 point. Oh, we don't have a t though. Ha 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 ha. Okay. So from here, we just need a t. This angle, so this is the t, this is t final specifically, right? At any given time t, yeah, this angle, this corresponds to final velocity. This is final, therefore this is final. Let me write those. This is final. This is final. Yeah. So how long did, let's see, what else can we do? Oh, I guess we get back, maybe I don't want to say that. Rx of t. Yeah, if we now bring this back, so we can say, okay, let's look at our horizontal position. That is awful. Let's look at our, obviously it's getting late. My handwriting is suffering. So here's our horizontal position equation, right? But if we want to know the final, right? So final position, that's just 60, was it meters? I assume it was meter. This is all in meters, right? 60 meters, yep. Final position was 60 meters. We still don't know that initial velocity, but we want to know time. And so what we can do, we can solve for time, right? So we divide by VO, divide by VO. There we go. And so we get that TF is equal to 60 meters divided by whatever that initial velocity is. And now we can take this value and plug that in to right there. And then we can get VO is equal to negative G. Here, I'm gonna write this as negative G times TF times 1 over tangent of 3 degrees. That tangent that 1 over tangent of 3 degrees is just some number. We'll calculate it when we calculate everything else. So we're just sort of carrying it around for right now. So this will be negative G times 60 meters over V times that 1 over tangent 3 degrees. So I'm going to rewrite this one more time. Actually, you know what? Here's what I'm going to do. Here, hold on. Pardon me. We're going to go back just a tick. There's a better way to rewrite this. We're going to rewrite this as negative g over tangent of 3 degrees, like that. So this is all the constant stuff, and then times t, whatever our final time is. So now when we go to plug this in, we won't have fractions within fractions. We'll have avoided that. Times, and now this is 60 meters over v0, right? Times TF, and then I'll write this as 60 meters over v0. There we go. Just to sort of color code it, say what's happening. Okay. And now notice we have, this is all constants over here. And we want to get that v naught over the other side. So we're going to multiply both sides by v0. Boom, boom. Times v0. Actually, here, let me do that in a separate step. So now we want to so we have v0 is equal to negative g over tangent 3 degrees times 60 meters over v0. And so we want to get this v over with the other v, like that. So we end up with v0 squared is equal to this. $60 meters. So we take a square root, right? Square root, and we get v0 is equal to the square root of negative g over tangent of 3 degrees times 60 meters times 60 meters. I can make that bigger. Times 60 meters. And then we can plug in our g. v0 is negative 9.8 meters per second squared over tangent of 3 degrees times 60 meters. So you can see what we're going to get. We're going to get meters times meters is meters squared over seconds squared. Take the square root, you just get meters over seconds, which is velocity. So our units are going to work out correctly here. And so now we can just plug that into a calculator, and we get v of 0 is approximately, so if we do, square root of negative 9. Oh, you know what? We don't want that negative in there. Would that negative have canceled out at some point? Oh, this y is negative. Anyway, right? This y up here is negative, so we would have a negative. So the negatives cancel out, and we get a positive. Boom. There we go. Right? It's a downward velocity. We know that because of the downward acceleration, so they sort of cancel and give us a, yeah. So we don't have a negative there anymore. Um, divided by tangent of 3 degrees, we'll do times 60, and it's all inside a square root. It is. And so I get 105 0.9, and the units would be meters per second, right? Meters squared, seconds squared, square root, so just meters and seconds. However, I don't think we get that many significant figures. If we go up here, 3.0, that gives us 2 significant figures. 45 is 2 significant figures. Yeah, so we sort of get 2 significant figures here. Which would sort of round this to 110 meters per second. I'm gonna leave that up to you and your teacher, right? Like however you all are dealing with significant figures. So uh, it looks like we should have 2 sig figs, right? So it should be V0. So you might round this to 106. 2 sig figs would be 110 meters per second. So whatever version of that. So our conclusion then is the arrow must have been fired. Do you fire an arrow? Launch? Shot. So been shot with an initial horizontal velocity of 110 meters per second, or 106, or like the 105.9 we found. 110 would be the correct significant figures for this. The arum, that's an upside down W. The arrow must have been shot with initial horizontal velocity of 110 significant figures. Fascinating. Okay, so let's go back. Let's recap, right? So we have an archer shooting an arrow horizontally, so it has 0 vertical initial velocity. So all of its initial velocity is purely horizontal. It's going to gain vertical velocity as it falls. Gravity is going to accelerate it downward, right? But it's not going to. So it's only going to gain total velocity. So we didn't really talk about that, but that's one of the consequences of this, right? It's not going to slow down vertically or horizontally, and it is going to speed up vertically as it goes downward. So it's going to gain total velocity. Anyway, initially horizontal. It strikes the ground, and the arrow, because it sticks in the ground, preserves the impact angle, which was 3 degrees, we're told. So we can set up a velocity triangle, right? And say, oh, okay, well, then if we do a ratio of the vertical to horizontal velocities, that's just that should equal whatever the tangent of that impact angle is. And we set up that equation. Tangent of 3 degrees equals Vy over Vx. But remember, our Vx is our initial velocity. So any place we see Vx, we can just replace it with Vo. And so we get this equation. However, we have 2 unknowns here. We don't know that final impact velocity, vertical velocity, and we still want to find that initial total initial velocity or initial horizontal velocity. Okay. We VO Um, oh yeah, this is, okay. Um, maybe I want to change this notation just a little bit. I was just looking at this. It's not exactly clear how we get from there to there. Um, um, so this whole thing goes here. We're just solve for VO. There we go. Oops. This is VY. And I put a little F on it because it's the final VY, right? It's the final velocity. And so we're like, oh, okay, so let's look at our kinematic velocity. What's the relation? We know that our we can rewrite, or we know how we can write our initial vertical velocity because it just depends on gravity. So it's just going to be gravity times time. So we replace the Vy with gravity times time, right? So we're essentially getting rid of that Vy variable and replacing it instead with T, which is a variable we're already dealing with, right? So we've basically gotten rid of a variable. Okay, now we have that and we simplify it a little bit, right? We rewrite it. All we've done is rewrite this. And we have this unknown T. Well, we know how far the arrow goes horizontally. And so we can look at our horizontal position equation and plug in that final position, 60 meters, and then solve for TF, solve for the time, and we can know that that time is just going to be that distance divided by that velocity. And so we replace it. We rewrote this so that when we replace it, it's a nice equation for us. And look, now the only unknown in this equation is v0, our initial velocity. So we multiply it over. That makes it squared. So we have to take a square root. But we do that, and we just work out the rest. We plug in our numbers, and we just calculate, right? So like I don't think there's really a big lesson in this problem other than the fact that you have lots and lots of tools at your disposal for solving complicated problems. You can, anything that's two-dimensional, you can decompose it into one-dimensional equations and look at them separately. And sometimes you know some things about one dimension but not the other, and you can leverage that. Then we also have various kinematic equations. We have the ones we looked at in the last problem, the kinematic equations for position, but there's also the kinematic equations for velocity. So we can leverage that as well. And so remember, you just have all of these things at your disposal. And what you're sort of looking at is, what are my unknowns? What are my knowns? I need at least as many equations as I have unknowns, and I need to be able to, like, you sort of use equations to sort of pivot around. You solve for one of the unknown variables so that you can substitute, so you can replace it. And now you've gotten rid, because you've substituted for it, now it's not part of the equation. And so that's the strategy here, right? Um, I think a really good question to always ask yourself when you're getting help from people, when you're watching somebody work out a problem, is, how would I have known to do that, right? And uh, now that you've seen it, so like before you watched me do it, you know, how would you have known to do all these steps? You wouldn't necessarily. They wanted you to sort of struggle through it and problem solve and try some things that didn't work. Um, and try to put it together. Unfortunately, that's sort of contrary. That sort of butts up against the fact that you need to get a good grade in the class, and you don't have hours and hours and hours to spend on your homework and stuff like that. So I totally get that. Um, so, but what I'm hoping to to demonstrate here is the type of options you have available, so you don't feel like you're floundering the next time you encounter a problem like this. You're like, okay, well, what are the things that I know, right? Because there's ultimately a limited pool of these tools. It might seem like a lot, but it's the same tools every time, and there are actually only so many of them, right? You split it into different dimensions. For each dimension, you can use the various kinematic equations, and then you look at like what information do they give you. Given information takes away unknowns because those become known values. Yeah, so that's sort of our process there. And I think that's a good place to leave the stream. We'll get rid of that. I mean, yeah, it's almost the end of the stream anyway. I'm going to assume I didn't get any questions in because there's nobody popped in to watch. So, we'll check. Okay. Cool. So I'm gonna get myself ready for the next stream, and then I want to, message my students and tell them these notes are available to them. So let's go over here. Next math help stream Wednesday at 3. Oh shoot. No, I can't. I think I have a conflict tomorrow. I do. I won't be able to do my stream tomorrow. So next math help stream is actually going to be on Sunday. Sunday at 11 a.m. PST. So yeah, we'll be back Sunday for the Sunday chill stream. Easy peasy. Next math help stream Sunday at 11 a.m. PST. There we go. Excellent. Well, that's ready to go. And I think that's all for me. Yeah, I'm glad we had some good stuff. I guess, as always, at the end, I will reiterate again, abolish ICE. Simple as that. We keep fighting for it. We keep pushing for it. And then we'll keep fighting and pushing for more. I hope you all have a good night and a good rest of your week. Send in your questions. I'll be back on Sunday.